Welcome back to Chips and Salsa, where we talk security at Intel. I'm Jerry.
I'm CRob.
And hey, we're joined today by Anders Fogh and Daniel Gruss from TU Graz. And we're going to talk about your talk today at Black Hat, which is Microarchitectural Vulnerabilities, Past, Present, and Future. Mm-hmm. But let's start with some introductions. Can you guys tell us who you are, what you do?
Yeah, so I'm a professor in Austria at TU Graz. I research microarchitecture and side channels, system security in general, all kinds of stuff. I have a team there with brilliant PhD students, currently 5 PhD students. And, well, I did like doing the research myself when I was a PhD student, but then you become a professor and realize, oh, you're not going to do the research anymore. No, it's but it's fine. It's about teaching the next generation, right?
Yeah. So I work at Intel. I work as a security researcher. I run a team that do security research, including on microarchitecture. Super interesting. I don't get as much hands-on anymore either, but we get a lot of stuff done.
Yes, you guys both did. I mean, I think you're both being a little humble in your origins here. I mean, you guys were both involved in the original discovery and publication of Spectre and Meltdown. Talk about that a little bit.
So, yeah, when we were still a bit more hands-on, actually, we on several occasions worked on the same topics. That was initially that was a bit funny. But then at some point it got really frustrating because like every time I was working on something, I was messaging Anders, okay, here, I'm working on this new thing. What do you think about it? And he was like, oh, I was planning to publish a blog post about this tomorrow. I was like, oh, no. And this happened 2 or 3 times. Yeah. And then we decided on one occasion, okay, come on, let's write the paper together. And that was that the prefetch sidechain attack?
That was a prefetch sidechain.
Yeah.
So the first talk Daniel and I gave here at Black Hat, we spent the night out drinking beers and discussing what would become Meltdown.
Yes.
So that was in 2016. So it was a bit ahead of our time at that point in time. But we caught up to it later as well.
Anders pitched this idea to me that you can just access some kernel memory and then maybe do something with it. And I was like, Anders, I've been teaching operating systems since 2010. Students do this all the time by accident. And no one ever saw any leakage or anything with that. They get a page fault, the process gets killed, and that's it. And I think at that point, I ended the conversation about that in some way. And that was maybe a mistake, yeah. Because that was in 2017.
We picked it up later.
Yeah, 2016, actually.
2016.
2016, yes. 2016.
So we picked it up apart from each other later.
Yeah.
And then came to the same results.
Yeah.
So as Jerry mentioned, you guys have been involved in this space for a while, and side channel attacks are interesting. It's obviously sparked a lot of innovative research. But maybe the two of you contextualize what a side channel attack is. Maybe just kind of give us a little bit of the history up until today. Just a brief.
Side channel. For a long time, like the question, what is a side channel? If you would ask 10 academics, you would get 10 different answers. I've been trying to bring it down to one definition that works for all the different areas. And my definition is obtaining metadata and deriving data from it. So you always have these 2 steps. You have a channel where you get metadata from, and then you derive data from it. And the second part, this is, I would say, a probabilistic step. So you never have 100, or you can get arbitrarily close to 100% maybe, but you never reach the 100% in general in this derivation from metadata to data. One example would be website fingerprinting. If you can observe Wi-Fi packets, you see the packet size. The packet is encrypted, so you can't see the data, but you have the packet size. And then that's metadata. and you infer which website was visited, which is data, which is encrypted information, but you can infer it from the packet size. It won't be 100% accurate, but you can take a good guess.
I felt like we needed a drum roll when you gave that simple description.
There is a lot of complexity below that statement, though.
Yes.
Totally agree.
So you guys are aware of, you guys are actually participating in a lot of the current research on software-based attacks on processors. Tell us something about that.
I think it's still a relatively new field. With new field, I mean, it really started taking off in 2005 with the first attacks on cryptography.
Mm-hmm.
And then sort of slowly started up more and more. So my favorite paper in that time frame was 2015 on breaking RSA with cache attacks. And then I think the watershed moment was sort of like 2015, where you got Rowhammer coming out, and we're starting looking more at attacking other things than cryptography.
That was when I had my first paper in the PhD, also targeting something that was not crypto with cache template attacks. Yeah. That was a change in perspective. And I think this is also very important about the context of these microarchitectural attacks and side channel attacks. What is the threat model? What is the thing that you want to attack, that you want to leak? And what is the environment? Like, where does the attacker sit? What can the attacker do?
And this is when you infer sometimes tiny bits of data. For most things, that's not relevant. And the reason why people started looking at for cryptography was exactly because in cryptography, tiny bits of information is important.
So thinking about these attacks, I understand that from a research and kind of a future-proofing idea, it's very important. But from a practical standpoint, so from the types of threats that a normal computer user would face, how practical are these types of side channel microarchitectural attacks?
Mostly they're on the difficult side for an attacker. There tend to be reliability issues with them. There are differences in hardware matters a lot.
Yeah, the environment is a problem, right? There are some attacks, you get them to work really reliable on one system. You run the attack on a system that you believe is identical, and suddenly it stops working. Sometimes it's really, really tricky. There are exceptions. There are things that work really reliable. For instance, I think flush and reload is one of the techniques that has become super, super widespread because it's so reliable. It's really, really reliable. And yeah, this is flush and reload actually has its 10th anniversary this year. Next week at Usenix Security.
So a lot of the research reports we've received at Intel so far this year are mitigated by current guidance, right? Like, so we have software guidance, for how to mitigate side channel attacks. Is that kind of what you're seeing these days? Or I guess where also is the research going in the future, both on attacks and mitigations?
So the future is likely to be determined by what offense can get done, right? That has always been there. It's true for software things as well. It's what the offense can come up with that determines where the defense goes. That said, there is some guidance, as you said, and those are mostly for the lower end of the spectrum. The higher end of the spectrum, the more serious vulnerabilities tend to get mitigated, usually in microcode patches. There are sort of the middle group, the Spectre of this world. That is, Spectre is ironically super important for the performance of computers. So it's not just something you turn off.
Mm-hmm.
It's factors, not percentage of performance. So all vendors are going to have a hard time with that. And there's going to be software solutions to that, to to that space.
And a lot of academic research also. I mean, we need to figure out what we really want there, what the user, what the developer really can express and communicate to the system.
And I think we will figure out how to do things better and efficient in microarchitecture. We're not quite there yet, but we're going in that direction. I think we are getting better.
Yeah.
You'll also see that some features, another vendor than Intel came up with a new kind of value prediction, and they delivered it with a switch where you can just switch it off if you don't like, if you don't prefer the security. And I think configurability of your security performance trade-offs is something that we're going to see in the future.
Yeah.
So there's a lot to it. There's also, so on the defensive side, we're starting to understand these problems in depth, and we're just going to sort of the things that can just be avoided. We're going to be avoiding a lot of those, and I think we're already seeing those effects. It has been quite a while since we had a stale data vulnerabilities in Intel, for example. Last year, we were down to 8 vulnerabilities on our CPUs for the entire year. And that has a lot to do with us figuring out how this actually works.
Mm-hmm.
Awesome. So you both have touched on it a little bit, but how do some of the newer technologies like GPUs and NPUs kind of fit into, are you thinking about exploring those areas? And what do you think you might, how will that complement what your historic research has been?
So I think if we talk about the term microarchitecture, it's always a question what we mean with that. In general, I would consider microarchitecture anything that is hidden behind some architectural interface, where you can say, well, from generation to generation, I can keep the same kind of architectural interface, or even if I don't keep it, like the architecture is the promise that I make to the other layers. It's the interface. And microarchitecture, for me, is everything behind that. And that means also these NPUs, these GPUs, they have an implementation. They have something that is behind the interface that is not specified for whoever is using that interface. And at that point, you will have behavior behind that interface that one can exploit. And this will be, again, side channels. It depends on the threat model again. If I'm able to interface the GPU or NPU, do I already have privileges? Then the question is, okay, is this super relevant as an attack vector then?
I'd say NPUs and graphics is not new territory for me.
Yeah.
We've been working on it for years and have shored up our graphics adapters quite a bit. NPUs is, of course, relatively new to us, but it's not like we haven't done security assurance on NPU. What we're going to see is a lot of development in those areas. And the more you develop, the more bugs you will find, right? And my job is to find it before the product ships to the customer. So my job number one. So we're going to see a lot of things in this area. There's going to be a lot of new workloads. The way we're doing compute is generally changing in the moment, where we used to have this general purpose CPU for everything. We're now seeing special workloads getting special things. The graphics was sort of the first generation, but now we have the NPU. We have all kinds of accelerators for all kinds of different scenarios, video encoding. And it's just, I think that development is going to continue at least for a while. So we're going to see lots of new kinds of microarchitectures, new assets to protect.
And I think this is where even if we try to protect these assets, that's where the problems come in. Because if you have a lot of interfaces, typically, if you have interfaces, someone is overlooking what happens on the other side of that interface. I mean, that's a lot of the attacks that we have been doing is, someone looked at the interface and thought, oh, that's secure. But then if you look behind the interface, it doesn't work anymore.
And it's true for human interfaces as well,
yes.
Right? So it's 90% of what we find is in the interface between something.
Mm. And we will get more interfaces necessarily.
And we will
That's
get more
part of complexity, abstracting away complexity, and then you have an interface.
But I think we learned a lot from the general purpose CPU about how we do this job. So it's not, we're not starting from scratch. We're starting from a relatively comfortable position. The past sort of 10 years of research has shown what it actually looks like.
I think the future in that sense might still have some unique new challenges also. I believe that the compute power that we have, like diversification into something like NPUs and GPUs, so that you can adjust to the specific workloads that you have instead of using a general purpose CPU. That's for sure something we need to do, because we can't arbitrarily scale up our general purpose compute. Right? We have limitations there. We have growth there in compute capacities that's slowing down. So we have to resort to these other techniques, or make our general purpose computers also more clever, add more features, optimize further based on what they are computing on, and not just generic optimizations.
You're absolutely right. And it will not be one or the other. It's going to be both, right?
Yes.
The general purpose computer are going to get faster and better and more powerful.
With more complexity.
But adding a ton of different kinds of compute to the same package or outside of the package is not just, and it's not just compute, right? It's how we do things. Moving from having a network adapter to using a smart NIC, for example, is another example where you basically add compute to something that was in the past.
Having compute and memory techniques, right? Using these compute and memory, new DRAM.
I think as we kind of wrap this up, I wanted to just kind of talk about the elephant in the room that's usually the misperception of the outside world, that companies like Intel and academic research are butting heads against each other. But we found, like, just the two of you being here talking together, the history between you is saying something a little different. What is it like as an academic researcher working with a company like Intel on these kinds of, complex problems?
So when we started with this, our joint history on this started actually in 2016 with the prefetch sidechain paper that we mentioned before, that we also presented at Black Hat. And back then we actually sent proof of concepts to Intel. And I would say back then, Anders, you weren't at Intel back then. You only joined Intel later in 2019, yeah. 18, 19, I don't know.
18.
Years later.
And we sent this to Intel, and the response was, can't reproduce. And I totally can understand it, because our description was, this is a prefetch sidechain attack. It works with the prefetch instruction, which was completely wrong. It was completely wrong. It was working, though, because it was speculative execution.
Okay.
We were actually exploiting Spectre v2 in this case, and we didn't know it. And I can totally believe that whoever tried to reproduce this couldn't reproduce it, because we also had systems where it didn't work and where somewhere it worked. So I can totally believe that. But back then, I would say processor companies in general, it's not just Intel, it was a bit more tricky to get them convinced that the thing that you're reporting is something relevant. This was still going on through, I would say, 2017, 2018. And then with 2018, through 2018, there was a big shift. And then in 2019, I would say since 2020, the communication with Intel has been really, really good. We had several disclosures since, and it was always very, very cooperative, where both we share what we have. Even if we have very early reports, we can share them with Intel. And in some cases, we even got information back like, okay, this what you found there is not what you thought it is, but it's something else. Sometimes this works, sometimes it doesn't. But overall, I'm quite happy with how the state of communication currently is.
I think on our side, it was just a realization it's much easier to work with people than against them.
Yeah.
I mean, there's things that we can't and won't contribute to, but in general, working with people is just much, much easier than working against them. And it just produces better results, not just for the academics, but also for our customers, and just makes life easier to work with people.
My impression was also that over this time, again, not just Intel, but multiple of these processor vendors more and more understood what the incentive structures for academics are. Like in the beginning, the first things that we reported, like one of the first emails typically was something like, yeah, but you won't get any bug bounty for that. And like, I don't care about the bug bounty. I'm doing research, and I have the funding for the research. So I just want you to figure out, does it make sense? And are we overlooking something? Can you acknowledge that this is an actual issue?
Nowadays, the first question that academics get when they report something is, when do you plan to publish?
Yes. Which is a good question.
And it's a super question because it sets the timeline.
Yes.
Right? And if you can keep that timeline, you won't have any problems with working with academics.
Yeah.
So it's the natural question: when are you going to publish? And that sort of catches the incentive that is in academia.
And the win is important, right? Because you got conferences, when you publish your papers, people are pursuing their PhDs.
Mm-hmm. The publicity is important for us, like publicity in terms of publishing the research. This is the more formal thing in academia. If you don't publish papers, you can't get a PhD, right? At least in our field. And then you need to make sure that people see your research. You need to have follow-up papers. You need to present it at conferences. If you want to make it visible, maybe you need a website, a logo, a name, right?
And the simple question about when do you want to publish just sets up everything that comes after that, right? That's what they care about. And then you can work towards getting things done by that deadline.
Mm-hmm.
Sometimes we can't get it done by that deadline. That's the unfortunate thing, is that hardware is really hard. And then mitigations are really, really hard because there's no sort of root cause fix. You're always trying to work with what you already have, and it makes it sort of difficult. But most of the time, we are actually getting things on time, and it works super well.
Well, I really appreciate both of you. We've talked several times in the past, and it's just a pleasure to see the conversation between Anders and Daniel, and allowing us to kind of record that and share that with our audience. And thank you for your past research and your continued future work. This is great.
Yeah, and good luck with your talk here at Black Hat.
Thank you.
Thank you.